In the previous video, we had discussed how SPICE calculates voltages and currents in a circuit, and we had mentioned that it uses your typical nodal analysis to write down currents, write down equations, and solve those equations for voltages at different nodes. Now, in this video, we'll see how do KCL and KVL compare with each other with regard to solving these voltages within a circuit. So KCL stands for your well-known Kirchhoff's current law, and KVL is the Kirchhoff's voltage law. Now, if you use KCL, the nodal analysis, it involves writing nodal equations at each of these nodes, as we mentioned previously. And instead, if we use the KVL, then it will use your well-known mesh analysis. And in this video, we'll talk about what are the key differences between these two approaches. So let's again use the same example where both these approaches are tried. Now let's start with the KCL case. Here, as we know that it is very much straightforward to set up these equations at each node. And for example, in this case, here we have three nodes that are there in this circuit in addition to the ground node, right? We are going to see the nodes that are in addition to your ground. So each node will have one equation, that much is understood. And how this simulator or SPICE basically handles this kind of a situation is that whenever it encounters a node in a netlist, okay, so SPICE basically scans the netlist from top to bottom. We did discuss the SPICE netlist in our previous videos. So while scanning the netlist, whenever it comes across a node that is mentioned in the netlist, so what it does is that if that node has already been mentioned previously, then it adds a term to the equation, to the nodal equation for that node. And if not, if that is the first time, the first mention of that node, then it writes a nodal equation for that node. More of it will be clear in this example. Let's take a look. So it's the previous circuit, previous schematic that we showed. So if, for instance, this is the netlist that we have written for the circuit shown in the previous slide. So we have a resistance between node N1 and N2, and the value is 5 ohms. Similarly, we have another resistor between these two nodes with a different value, and so on and so forth. Okay, this is the netlist description of our circuit schematic in the previous slide. So as SPICE goes through each one of these netlist statements, so statement number 1, 2, 3, okay, so once it checks, for example, this statement in the netlist, what it sees is that it encounters two nodes, node N1 and node N2. So it has encountered two nodes, so it will write an equation. See, here it is encountering both these nodes for the first time. So it is going to write an equation, a nodal equation for this node and this node, like this, in this form. So this is the overall complete equation for node 1. But what I am going to show is that the flow of this netlist scanning. So as it encounters N1, so it will just write this thing. So between N1 at N1 and N2, we have this element R1. So it will only write this one, V1 minus V2 by 5. Just this much, as soon as it encounters N1. Now note, this equation is for node N1. But since this statement also has node N2, so it will also write another equation. But not this full equation. It will only write this thing, V2 minus V1 by 5 is equal to 0. Okay, as long as it only sees this statement, first statement. Okay, 1 second. Okay, yeah, so what it does is that it sees N1 and N2, it will only write this much, equate it to 0. This is the equation for N1. This is the node N1, right? and then since it also has, this statement also has n2, so it writes this much, v2 minus v1 by 5. Why this? Because this is corresponding to resistor r1, which has a value of 5, so it will write this much is equal to 0. Okay, let's go to the next statement. So next statement is r2 between nodes ground and n2 with a value of 10 ohm. Now it is seeing, and it is seeing n2 now, not n0, because this is ground anyway. Okay, so what it sees is that n2 and n0, between these two nodes we have a resistance of 10 ohms. So it will update the equation that it has already written for n2. So this was the equation that it had written for n2 with just this much entry, right? So it will add this value, v2 by 10 plus v2 minus 1 v1 by 5 is equal to 0. Okay, no mention about this thing yet because it has not seen anything below r2 for now. Let's consider, like, okay, let's move to r3 now. Okay, it goes to third one, so it sees node n2, so it will make an entry corresponding to node n2. What does it do? So it writes this thing, between v2 and v3 we have a resistor r3 with a value of 5, so it enters this term, third term, and the equation for n2 is complete now. Okay, at the same time, since it is also encountering the node n3, so it writes a new equation for n3 where this is the quantity that it enters, v3 minus v2 by 5 is equal to 0. Okay, next it goes to fourth statement. Here it sees n0 and n3, so n3 equation already you have this much. Now it sees between n3 and n0 we have a resistance 10 ohm, so it adds this term. Okay, and finally it sees this last statement and adds a corresponding entry here. So that's how you get these three equations. This is the algorithm that SPICE follows in writing down these nodal equations. Okay, this is if you use KCL. Now if we want to use KVL for the same calculation, if you want to do the same analysis using KVL approach, then note that KVL relies on the mesh analysis done for all loops. Okay, you have to find loops within the circuit. Now note that it's not easy to find out how many loops you may have in a circuit, because if you compare with the nodal analysis, you can easily find out how many nodes you have in the circuit, right? As many as you see in the schematic, you have that many nodes in the circuit. But it is not so easy to find out how many loops you have, because you have a smaller loop, then you may have a bigger loop, you may have an even bigger loop, and that's not as straightforward. And for that you need to use graph theory and certain algorithms to find out those loops. Okay, now using algorithms, graph theory, and remember that SPICE was developed in 1970s. Okay, back in 1970s you had graduate students at UC Berkeley who were working on SPICE engine development. Now it wasn't straightforward, it wasn't an easy thing to be done at that time using algorithms, computation, and such stuff. It was difficult, and more importantly, why did you want to give pains to graduate students? You don't want to load them with unnecessary work, because the previous approach that they found using KCL was good enough to sort out or to find out the solution for their problem. So this doesn't add any value using this kind of an approach with more tedious kind of an effort. So it doesn't serve any purpose. So therefore you will see SPICE is based on this kind of an approach, KCL, because this is much more straightforward and simpler. Now, how does SPICE solve nonlinear circuits? I mean, elements that are nonlinear. For example, you have a diode. Okay, diode is not a linear element. A resistor is a linear element. Okay, but diode is not a linear element, because the current voltage relationship is not linear. That is what we mean by a nonlinear element, because current in a diode goes like this thing. Okay, it goes as an exponential of the voltage that is applied across its ends V1. For example, note that in this circuit we only have one node. This is a very simple circuit. We have a current source, we have a resistance, and then we have a diode. Okay, so we only have a ground node here and a node N1 here. We don't have three nodes here because all these, they are shorted. So this is one single node. All right, now if we want to write the nodal equation, so we will only have one nodal equation because we only have one node, so we will be having this sort of a nodal equation. So 5 amperes plus this current is equal to 0. Yeah, now this isn't as straightforward because even though this is a single nodal equation, single KCL equation that we have to solve, but it is a transcendental equation. So what do we mean by that is that we cannot separate V1 out in this equation to find a solution for V1. That's not possible. We will always have V1 as a function of V1. Okay, that kind of an equation which is in which a variable is a function of another the same variable, that is known as a transcendental equation, and it cannot be solved explicitly. So it has to be solved using some other method. Okay, and that method is called a numerical solution. And modern these computation, it involves use of certain algorithms for handling these kind of problems. Now if we want to use this kind of a process, for example, this this non-linear equation we want to solve, and if we want to go using the traditional method of using GV is equal to I, as we have already always been doing using these elements. So GV is equal to I, what it will give you is this thing, right? We will get this kind of a matrix kind of formation for this previous equation. So this equation, if we write the same equation in the form of a matrix, this is what we'll get. So this is the G matrix, so this is V, and this is the I matrix. Now note that the I matrix is not a simple constant or a zero. In the previous examples, simpler examples, we had either a non-zero value or a zero, and that was very easy to handle. But now what you have is that this I matrix has, even though it has a single value, but this value is not a constant or zero. It has V1 in it, and V1, this V1 depends on this whole thing. So therefore it's not that straightforward. Now how do we solve this kind of a problem? So in this case, as you see that since we only have a one cross one kind of a matrix, okay, so this is a very simpler one, so we don't need to find out, we don't need to go through the Gaussian elimination as we discussed in the previous cases where the matrix was 3 cross 3, and in order to simplify the matrix we use Gaussian elimination and find out values for voltages at different nodes. But here, even though we have a single node, so we don't need Gaussian elimination, we just need to find out the value of V1. Okay, but V1 cannot be found out directly because this equation is transcendental. Okay, and in order to solve this, there is a very well-known algorithm which is called Newton-Raphson's algorithm. I'm sure you must have come across this using a course, mathematics course on numerical methods. Okay, so Newton-Raphson, what it does is that it uses this very simple approach where finding a value at an iteration n plus 1 can be done using the value known at an iteration n and the function using the value at iteration n. Okay, so this is the function, this is the derivative of the function, and we plug in the values and find out the value corresponding to the next iteration. And once we have found out this thing, we plug it back here. Okay, and we plug it back here, calculate the value for n plus 2, and so on and so forth, as long as we make sure that the two continuous iteration values that we obtain, they are fairly close enough, or close enough within the permissible values. Okay, for example, I'll show an example and that will clarify. Now Vn plus 1 is the voltage at the next iteration, right? And Vn is the voltage at the present or current iteration. And make sure that you do not confuse this n plus 1 or n with the nodes that we are showing in the schematics, those n1 and n2 and n0. So this is not that. This n here stands for an iteration. Okay. Now, for example, let's go to the previous case where we were having this equation phi minus diode equation, diode current minus 0.5 V1. Okay, this one, this equation. So this is the main equation. Now, in this whole equation, except the zero, this becomes the function f. Okay, so this f is that equation, and we just replace v with v1 with vn. Okay, so this is the first iteration value. Okay, so f of v1 is given by this whole thing. Yeah, and at the same time we calculate f dash of v1. So we do the derivative of this thing. Okay, we differentiate this also one time, and we plug in the value of fv1 and f dash v1 in this equation. Okay, what we get is something like this. So this is the general representation of what would be the value of an iteration n plus 1. So it will start with the value at iteration n minus f divided by f dash. Okay, so we'll keep on doing this process until the values vin and vin plus 1 are fairly close to each other, or the error between them is tolerable. Okay, that's where the concept of tolerance comes into picture. We'll talk about that also. So for example, let's say the supposed value of v should have been 0.5 volts, for example, and what we get here is 0.495 volts, for example, and then this next one is 0.497 volts. Okay, and we keep on doing it. Now we can say that, okay, we wanted to have the actual value of 0.5 volt, but if you have a tolerance of 5 millivolts, then we can say that, okay, the value that we have obtained is correct. So it depends on how many iterations you do, and therefore you can have a trade-off between the number of iterations and the tolerance. So higher the tolerance or the stricter the tolerance, you need to do more and more iterations, or if you relax the tolerance, then you can get a value in less number of iterations. Okay, now let's take this example of a slightly larger circuit. So the previous case was for a single node equation. Okay, now here we have a larger circuit. Now note that all voltages are to be replaced with current sources, right? We did mention that in the previous video, so that this looks of this form, so that handling the current source allows us to get a current matrix, and we can proceed with the calculation for these nodes. Now let's say that this is a starting case. Now here we have two equations, two nodes. So we have one node here, we have another node here. So what we do is we straight away write the two nodal equations for node 1 and node 2. So this equation V2 by 10 plus this diode equation, diode current Is exponential of V2 by Vt. Now Vt here is the thermal voltage, please note. Okay, and V2 minus V1 by 5 is equal to 0. So this is the equation for this node. Similarly, this is the equation for this node. Okay, so we have these two equations. Now they can be written in this matrix form. Okay, so V1 and V2, this is the voltage vector, this is the conductance matrix, and you have the current vector. Okay, now next step is to use Gaussian elimination. So we subtract rho 2 minus rho 1 and all that stuff, you know that very well. So what we get is here is this thing. Okay, we get a 0 here, and that is all we want, because if we get a 0 here, then we can find out the solution for V2. But note, now V2 cannot be found out straight away, right? Because V2 is here and you also have V2 here. So this is this transcendental case that we mentioned previously. So this has to be solved numerically using Newton-Raphson. Okay, so we'll use Newton-Raphson to find out V2, and once we have found out V2, we'll plug that back in here and find out V1. Okay, that is how we can find out V1 and V2. Okay, Now, so given this background, what about L and C? How do we solve circuits that involve inductances and capacitances? At least for a more simpler case where we just have to find out the DC bias point, DC due to a simple DC simulation using inductors and capacitors. Well, it's very simple because capacitances are under DC conditions are seen as open circuits and inductors are set to short circuit. So this is a very simple example, but we'll do a more complicated example in our subsequent videos where we'll treat them as nonlinear elements. Uh, and with this background, and since we have some fair understanding of spice now and also the Newton Raphson, so this has set the stage for discussing some new interesting topic in spice, and that's about convergence, and we'll talk about that in the next video. So I'll see you there. Thank you.